If you read through this problem, you can see at the root of it, it is an empirical formula problem, but it's probably unlike ones that you have seen before. Because instead of it telling you like the percentage or the mass of each of these elements in the compound, it tells you how much carbon dioxide and water was produced when we burned a certain mass of this compound. So these types of problems are called empirical formula from combustion data. So just to review combustion reactions, you have a fuel, usually made of carbons, hydrogens, maybe some oxygens, plus O2. Oxygen is needed to support combustion. And then complete combustion yields carbon dioxide and water. But the problem here is you don't know what your fuel is. All you know is that it contains CH&O and how much total you have of it. So I can't write out a balanced equation because I don't know my formula here, and therefore I'm not going to know what any of my coefficients are here. But what I can do is say, okay, I have 0.105 grams of my compound, and all of the carbon in that compound is going to get converted to carbon dioxide. In addition, all of the hydrogen in that compound is going to get converted to the hydrogen in water. You can't say a similar thing for your oxygen because you have oxygen coming in from the air. So that's not going to be that helpful right now. Okay, so we're going to go for our green root here, figuring out the mass of carbon in carbon dioxide, because that's going to be the mass of carbon in our quinone. This is going to be a percent composition problem. So our percent of carbon in CO2, we're going to get these molar masses off the periodic table. So there's only one carbon, so it's going to be just the molar mass of one carbon, divided by the molar mass of the compound, of the CO2, times 100. So when you do the math, you should get 27.3%, and that's the percent of carbon in carbon dioxide. Then you can take 27.3% of your 0.105 grams of your compound. And what that will do is give you the grams of carbon in that compound. So I get there 0.0702 grams of carbon in the CXHYOZ. Hi, it's Mrs. Weck with a big old I'm sorry because I made a mistake. So what I just told you was totally false. This is the amount of compound you have, and I should not have had that number here. 27.3% is the mass percent of carbon in carbon dioxide. So we need to take 27.3% of the mass of carbon dioxide. Okay, so this is a big old X, and then we have 0.257 grams of the CO2, and then we can figure out the grams of carbon in the CO2, which also ends up equaling the grams of carbon in the unknown compound. Okay, so my apologies, and then I screw up again in the next one. Now here, there is some good news. The good news is this value was correct. I did it correct on my work beforehand, and then I messed it up in the video. Okay, so these numbers that I use are still correct. So your final answer is correct, but my explanation for what I did here was like, oh, so wrong. And I can't believe I didn't catch myself messing that up. My apologies greatly. We're going to do a similar thing for the percent hydrogen in water. I did a similar thing here, finding the percent hydrogen in water, and then taking that and multiplying it by the mass of the compound to get the mass that is just hydrogen. Okay, and I did it again. So we're going to cross this number out and instead get the mass of water, because 11.1% is the mass percent of hydrogen in water. So 11.1% of 0.0350 grams is this answer. So again, that answer is still correct, but my 0.105 grams of the unknown compound should not have been there because that's a false way of doing things. Now we have to find by subtraction the mass of oxygen. So we know we have 0.105 grams of the compound. We'll subtract out the 0.0702 grams that are carbon. We'll subtract out the 0.00389 grams that are hydrogen. And what's left over is going to be the oxygen in the compound. So that's going to be 0.0309 grams of oxygen. So here's the cool thing. Now you know how many grams of carbon, how many grams of hydrogen, and how many grams of oxygen you have. So this was all the hard part to getting to now a very simple empirical formula problem. To start our empirical formula problem, I'll just divide, well, I always start with over 1, so I'll just do the molar masses. So 12.01 grams of carbon in every 1 mole of carbon, okay? Because for empirical formula, you want to go to moles. So we'll get moles of carbon. We're going to do the same thing for the hydrogen and the oxygen. So I converted all of my grams to moles. Okay, so I have my 3 answers here, and now you have to pick the smallest one. So it looks like our moles of oxygen is the smallest one. I'm going to divide everything through by that number. So clearly we're going to have a ratio of 1 here. When I do it with my hydrogen, I get something really, really close to 2, and with my carbon, I get something really, really close to 3. So now we know that the empirical formula is going to be C3H2O. With some additional information that the molar mass of the quinone as it exists in nature is 108.1 grams per mole. Now we can actually find the molecular formula. We wouldn't have been able to do that if we weren't given the molar mass. So there's just going to be some multiplier that's equal to the molar mass of the molecular formula. It has to be a whole number multiplier that we find with this X here, divided by the molar mass of the compound, of the empirical formula. So just add up 3 carbons, 2 hydrogens, and 1 oxygen, and we get 54.05, and we can see that X is equal to 2. So what that means is that in nature, the compound is twice as heavy as what we got for the empirical formula. So twice as heavy would mean 6 C's, 4 H's, and 2 O's. So there's your molecular formula.